Okay, so when we look at large language models today, there's some pretty big hurdles, right?
Oh, absolutely. Huge ones.
You've got these just astronomical costs for scaling them up.
Right.
They're not very flexible once they're trained. And then there's the massive effort of retraining everything from scratch if you want new capabilities.
Exactly. It's not just inconvenient. It's really slowing down innovation, how we develop and deploy these things.
Yeah, a major roadblock.
Precisely. And that creates this, well, extremely expensive burden on the whole training process. And it really limits how adaptable these LLMs can be in different situations. This kind of rigidity, it's become a really critical open challenge for everyone working in AI.
It's a serious bottleneck.
Yeah.
But what if there's a different way to think about the architecture itself to, tackle these problems directly?
That's exactly what we're diving into today.
Right. So today's deep dive is all about this really interesting proposal, the chain of model, or COM idea, and specifically how it applies to language models, which they call chain of language model, or COLM.
This comes from recent research by Kai-Tao Song and colleagues over at Microsoft Research and Fudan University.
And our goal here is to really unpack how COM could offer, well, much better efficiency and flexibility for deployment, basically hitting those core scaling and adaptation issues we just mentioned.
Yeah, and what's really cool is how they introduce these completely new building blocks for models. We'll get into chain of representation, chain of layer.
Yeah, and column error too, right? Which sounds pretty ambitious for making inference more flexible.
Especially for those really long context scenarios. It's fascinating stuff.
Definitely. So let's start by laying out the basic problems the researchers saw with current LLM scaling. They flagged two main things. First, unlike how humans learn bit by bit, current scaling methods mean you have to train from zero every time if you want to add a new scale, but keep the old ones. It's just, well, it's not efficient.
Not at all. It completely misses that idea of incremental learning.
And second, current architectures, whether they're dense or a mixture of experts, they always fire up a fixed number of parameters.
Right. A fixed scale.
Which means they can't really adapt on the fly to different problems or, different amounts of available computing power.
And that fixed scale activation, that directly leads to not being able to offer different levels of inference usage depending on where you're deploying it or how complex the task is.
So adding features or scaling up means this hugely expensive do-over every time.
Yeah, and with models getting bigger and data needs growing, that's just not sustainable in the long run.
Okay, so that sets the stage for their solution, the chain paradigm. It starts with chain of representation, or core. The idea here is to think of the hidden state at each layer differently. It's made up of multiple sort of sub-representations or chains within the hidden dimension.
And the key constraint, the really crucial part, is that each output chain can only see the input chains that came before it. It's causal.
Ah, okay. Causal.
Yeah, and that causal design in core is what lets you encode, say, in different scales within just one representation. You just activate the first few chains you need.
Interesting. So how do you connect these core layers?
That's where chain of layer, or core comes in. It's the mechanism that connects core inputs and outputs. It makes sure you get this multi-scale transformation, but it strictly follows those core causal rules.
And COLA itself has some important properties.
It does. Three fundamental ones. First, generality. Any standard layer, like a linear layer, is basically a coral when n is just one, so it fits existing stuff.
Okay, backward compatible. Good.
Second, causality. This is key. To get features at scale I, you only need to compute the parameters for scales less than or equal to I. So theta is I.
Which avoids forgetting previous scales when you expand.
Exactly. It tackles catastrophic forgetting right in the design. And third, compositionality. If you stack multiple Corel layers, the whole stack still has the Corel property. It scales naturally.
Right. So putting it all together, a chain of model COM is when every single layer in the model follows that Corel property.
From start to finish.
So the model itself inherently contains multiple submodels at different scales, all packed into one unified structure, which allows for that progressive scaling.
Precisely. And that leads us directly to chain of language model, COLM, which is simply applying these COM principles to every layer in a standard transformer.
So how does that change the transformer architecture specifically?
Well, you replace the standard linear layers with what they call chain of linear layers. There's a hyperparameter C that defines how big each chain is within the dimension.
And they figured out how to implement this efficiently.
Yeah, they mentioned using a blockwise sparse kernel to make it practical.
Okay. What about attention?
Same idea. In multi-head attention, all the linear layers, query, key, value, output, get replaced by chain of linear layers.
And there's a detail about the heads.
Critically, yes. The sum of those C values for the chains has to equal the total number of attention heads, H. This makes sure each head only contains information from a single scale, sticking to the conal causality rule.
Got it. And the feed-forward network.
Same treatment, replace linear layers with chain of linear. Normalization happens per chain. And for embeddings, if you want scale A, you just use the embedding dimensions corresponding to the first I chains. It's truly multi-scale.
Okay, this is all very clever architecturally. But now let's talk about ColMR. This sounds like where the deployment flexibility really kicks in.
It absolutely is. ColMR is an extension, a pretty ambitious one, that adds this KV sharing mechanism into the attention part.
KV sharing, how does that work?
So the keys K, and values, V, are computed only using the very first chain.
Just the first one for everything.
Just the first one. And then those computed keys and values are shared across all the other chains.
Wow. Okay, what does that enable?
The implications are actually huge.
Okay.
First, you can switch between different scales of the LLM during inference, like going from a smaller version to a bigger one, with basically no extra cost for recomputing keys and values. That's normally a big overhead.
That's a massive advantage.
And second, it dramatically speeds up the pre-filling stage, especially when you have really long contexts.
They had results on that.
They did. The paper showed Colomere was like 1.6 to 3 times faster for pre-filling 1 million tokens compared to Llama baselines.
Wow.
And if you combine it with other techniques like minference, they saw up to a 27x speedup. It makes it really suitable for things like PD disaggregation architectures too.
Okay, the performance claims seem strong. Did the experiments bear out that Column models perform as well as standard ones, besides being flexible?
Yes, that's a key finding. The results show that the Colem family, including Colomere, achieves performance that's comparable to standard transformers, like the Llama 3.21b baseline they used.
So you get the flexibility without a major performance hit.
Exactly, and that flexibility shows up in a few ways. One is chain expansion.
Right, growing the model.
Yeah, Colem lets you incrementally increase the scale using an existing model as a base. No need to train from scratch. They even saw performance boosts over baseline models like Tiny Llama and Llama 3.21b doing this, even with limited extra training.
And the elastic inference.
That's elastic inference. Because Column M integrates multiple submodels, you can deploy one foundation model, but use different scales as needed. They gave an example. One Column model could act as both a 0.86 billion parameter model and a 0.33 billion one.
Offering different performance and cost points from one model?
Precisely. And finally, there's chain tuning. This is a neat fine-tuning trick.
How does that work?
You freeze the first few chains, the core knowledge, and only fine-tune the later chains. This drastically cuts down tuning costs and, importantly, helps prevent that catastrophic forgetting issue.
Did it work well?
Impressively well on the GLUE benchmark. They boosted accuracy significantly by fine-tuning only about 42% of the parameters. And it plays nicely with existing methods like LoRa too.
That's very practical. Okay, let's put common in context a bit. How does it relate to something like mixture of experts, MOE, which is another way people scale models?
Good question. They're actually quite different in their approach. MOE typically creates multiple expert submodels that have roughly similar capabilities, and it uses sparse activation, only activating a few experts for any input.
Right.
COM, on the other hand, creates a sequence of nested experts. They progress in capability, like weak to strong, where each expert builds upon and includes the capabilities of the ones before it.
Nested versus parallel experts, kinda.
You could think of it that way. So they address different aspects of scaling. This means COM is fundamentally orthogonal to MOE.
Orthogonal meaning they aren't competing.
Exactly. They aren't mutually exclusive. You could, in theory, combine COM and MOE principles in a single architecture.
Interesting possibility. So where is COM best applied? Is it a replacement for current backbones?
Not really a replacement backbone. It's better to think of it as an innovative design for scaling architecture. It's about how you structure the model to grow and adapt efficiently.
And it works best for?
It seems particularly suited for large-scale models. A lot depends on that very first chain. It sets the baseline understanding capability, so it needs to be strong.
And it mainly applies to model width right now.
Primarily, yes, the hidden dimension. Applying it effectively to model depth, the number of layers, is still more of an open research area. Depth does something different, abstracting higher-level features. Plus, there are still some infrastructure challenges, like efficient tensor parallelism for COM models as they are now.
Okay, so wrapping this up, the core idea behind COM and Column is really this new paradigm. It's flexible, efficient, lets you build these multi-scale models in one go, and crucially, keeps what was learned before. No more starting from zero all the time.
Exactly. And for you, the listener, working with or deploying these models, this offers a real path towards more efficient and adaptable AI. Imagine architecting a model that can easily give you a small, fast version for quick tasks or a large, powerful version for complex ones, all from the same trained base.
Without the huge retraining costs or performance compromises we often see now.
Right, you get specific model sizes for different needs efficiently.
It definitely opens up possibilities. Which leads to a final thought. As we keep pushing what LLMs can do, what kind of clever infrastructure designs might we need to really take advantage of architectures like COM, especially tackling things like tensor parallelism limits? And how critical will designing that foundational first chain be for the ultimate understanding ability of these future models?